The universe is filled with chaos, destruction, and extreme forces. Out there, planets are being shredded apart by black holes, entire star systems are being swallowed by cosmic voids, and invisible bursts of radiation are powerful enough to sterilize entire worlds in an instant. If you think Earth has its fair share of disasters, imagine a planet where it rains molten iron, or a sun that can suddenly double in brightness and fry everything in its orbit. Worst of all, some of these cosmic horrors aren't just distant nightmares. Some, like asteroid impacts and solar storms, could affect us here on Earth, possibly within our lifetimes. So buckle up, because we're about to dive into the most terrifying things in space. Some real, some theoretical, but all guaranteed to make you appreciate the safety of our little blue planet. The unseen killers. Rogue planets drifting in the dark. Rogue planets drift silently through the vast cold emptiness of interstellar space, unseen and unpredictable. They do not orbit a star, nor do they bask in the warm light of a sun. Instead, they roam freely, untethered, like ghosts in the darkness. These wandering worlds are only detectable under the right conditions. Unlike asteroids or comets, which are small and often burn up in the atmosphere if they enter a planetary system, rogue planets can be the size of Jupiter or even larger. If one were to pass near our solar system, the effects could be catastrophic. Many rogue planets likely began their existence in a star system, forming just like any other planet. In the early stages of planetary development, young star systems are chaotic places. Massive gas giants can shift positions, and smaller planets can be thrown into different orbits. Sometimes gravitational interactions between planets push one of them so far out that it escapes the system entirely. Once this happens, there is no turning back. The planet is sent into the void, forever cut off from its parent star, left to wander through space without any light or heat. Not all rogue planets form this way. Some may have been born directly in interstellar space, forming from gas and dust that never coalesced into a star. Instead of circling a sun, these planets came together in isolation, having never experienced the warmth of a parent star. This could mean that rogue planets are even more common than we realize. If planets can form outside of solar systems, then the number of wandering worlds could be staggering. Scientists have attempted to estimate just how many rogue planets might exist, and the numbers are unsettling. Some studies suggest that for every star in the Milky Way, there could be several rogue planets drifting in the dark. That would mean billions, perhaps even trillions of these lost worlds moving unseen through space. Some could be no bigger than the Moon, while others might exceed Jupiter. Scientists have only been able to find them through indirect methods. One way is by looking for a phenomenon called gravitational microlensing. When a rogue planet moves in front of a distant star, its gravity bends the star's light slightly, creating a temporary brightening effect. By studying these brief moments, astronomers can estimate the presence and size of a rogue planet. This method has revealed a handful of candidates, but it is not precise enough to find them all. Some rogue planets may still give off a faint heat signature, especially if they are young and still cooling from their formation. Telescopes like the James Webb Space Telescope or JWST may help uncover more of these types of rogue wanderers. If a massive rogue planet were to pass near the Sun, its gravitational pull could disrupt the orbits of planets, asteroids, and comets. Even a close encounter could alter the trajectory of objects in the Kuiper Belt or the Oort cloud, sending deadly comets hurtling toward Earth. In the worst-case scenario, a rogue planet could even pass through the inner solar system itself, throwing everything into chaos. There is the possibility that a rogue planet could have already passed by in the distant past, leaving behind only subtle clues of its visit. Some astronomers have speculated that unusual orbital patterns in the outer solar system could be the result of a past encounter with a massive unseen object. While no definitive evidence has been found, the possibility remains that the solar system has been influenced by one of these wandering worlds before, and could be again in the future. If a rogue planet were lurking closer than we think, would we even know? The answer is uncertain. Because they are so difficult to detect, one could be approaching without warning. Some scientists believe that an object roughly the size of a planet may already be hiding in the outer reaches of the solar system, beyond the orbit of Neptune. This planet 9 has yet to be found, but its presence is suggested by strange gravitational effects on smaller bodies in the Kuiper belt. If we have such a hard time finding a long-lost member of our solar system, what hope do we have of finding a rogue planet? The prospect certainly makes for some terrifying food for thought. The death spiral, when planets fall into their stars. Some planets are not destined to drift alone through space. Instead, their fate is sealed by an entirely different force, a slow, inevitable fall toward the very star that once gave them life. These planets live on borrowed time, locked in a cosmic death spiral as their orbits gradually decay. Over time, they inch closer and closer until they are finally consumed in a fiery end. Astronomers have discovered several exoplanets that are on this doomed path. One of the most well-known is Kepler, 1658b, a planet about the size of Jupiter orbiting a star 2,600 light-years away. Scientists have measured its orbit shrinking, bringing it ever closer to its star. Over time, the gravitational forces between the planet and the star create tides, similar to the way the Moon affects Earth's oceans. But instead of just pulling at a thin layer of water, these tides stretch and distort the entire planet. This process slowly robs the planet of energy, causing its orbit to decay. The same effect happens on Earth, though in reverse. The Moon is slowly drifting away because of tidal interactions with our planet. But for Kepler, 1658b and other doomed worlds, it's the opposite. Each orbit brings them slightly closer, setting them on a path they cannot escape. Eventually, they will get so close that the immense gravitational pull of their star will tear them apart before they even reach the surface. Another planet caught in this slow-motion destruction is WASP-12b. This gas giant is so close to its star that its atmosphere is being pulled away, stretching it into an elongated shape rather than a sphere. The star's gravity tugs at it constantly, stripping away layers of gas and feeding off its own planet. Scientists estimate that within a few million years, WASP-12b will be gone, completely consumed or reduced to a lifeless core before finally vanishing. For gas giants like WASP-12b, the destruction is violent and drawn out. As they spiral inward, they experience extreme heating. The atmosphere expands, creating massive storms and high winds that rage across the planet. The surface temperature rises to thousands of degrees, causing the outer layers to evaporate into space. The planet effectively turns into a comet, trailing a tail of vaporized gas behind it. As it gets even closer, the entire world becomes unstable. Tidal forces stretch and compress the planet so severely that its surface may bulge by hundreds of kilometers with every orbit. Smaller planets, like rocky worlds, face a different kind of destruction. If a planet the size of Earth were caught in a decaying orbit, the immense heat from the star would first strip away its atmosphere. Without protection, the surface would be scorched, turning into a molten wasteland. As it moved closer, the planet would begin to break apart, with massive earthquakes and volcanic activity, as gravitational forces twisted its structure. In its final moments, it would likely shatter completely, sending a stream of debris crashing into the star. For an observer watching from space, the last moments of a planet's life would be extraordinary. As it approached its star, it would glow brighter, radiating heat and light. If it were a gas giant, its atmosphere might swirl away in spiraling tendrils before finally being swallowed up. A rocky planet might resist longer, breaking apart into glowing fragments before plunging into the inferno. The impact would be immense, sending out shock waves and possibly creating a brief brightening of the star as it absorbed the energy of the doomed world. The death of a planet can change the entire system around it. When a planet is destroyed, its gravitational influence disappears. Other planets in the system may shift in response, altering their orbits in unpredictable ways. If a gas giant is consumed, leftover debris from its atmosphere could fall onto nearby planets, changing their composition. Some scientists even believe that the destruction of planets could create unusual types of stars known as polluted white dwarfs. These stars show signs of having absorbed rocky material, possibly the remains of planets that once orbited them. Could this destructive event happen in our own solar system? The good news is that none of the major planets are in danger. But over extremely long timescales, things can change. The Sun is slowly losing mass as it burns through its fuel. This means that the orbits of the planets are gradually expanding. However, when the Sun reaches the end of its life and expands into a red giant, it will engulf Mercury, Venus, and possibly Earth. These planets will not spiral inward due to orbital decay, but will instead be swallowed as the Sun grows larger. Some planets drift alone in the darkness of space, while others are bound to their stars, destined to fall inward until they are no more. Whether through cold isolation or fiery destruction, the universe is filled with unseen dangers, shaping the fate of worlds in ways we are only beginning to comprehend. Coronal mass ejections, when the Sun attacks. The Sun is not a calm, steady ball of light. It is a roiling, turbulent sphere of plasma, constantly shifting and erupting with violent bursts of energy. Among its most powerful and unpredictable events are coronal mass ejections, or CMEs, massive eruptions of charged particles and magnetic fields hurled into space. When these waves of solar material are directed toward Earth, they can unleash geomagnetic storms capable of disrupting technology and altering the very fabric of daily life. CMEs begin deep within the Sun's outer atmosphere, where tangled magnetic fields build up enormous amounts of energy. When these fields snap and realign, they release an explosion of plasma traveling at incredible speeds. Some CMEs move slowly, drifting through space with little effect. Others race outward at millions of miles per hour, crossing the vast distance between the Sun and Earth in just a matter of days. When they arrive, their effects can be felt across the entire planet. The most famous recorded CME occurred in early September 1859, when astronomer Richard Carrington, busy observing the Sun, saw something extraordinary. A sudden flash of light erupted from the surface, a massive solar flare unlike anything ever recorded. Hours later, Earth was hit by an intense geomagnetic storm, causing brilliant auroras to appear across the globe. The night sky glowed so brightly that gold miners in the Rocky Mountains began preparing breakfast, thinking the sun was rising. But the storm did more than paint the sky with colors. Telegraph systems, the most advanced technology of the time, failed across continents. Some machines sparked and caught fire, shocking operators. Others continued to function even when disconnected from their power sources, overwhelmed by the electrical charge in the atmosphere. Modern technology is far more vulnerable to solar storms than the telegraph wires of the 19th century. Power grids, satellites, GPS systems, and even the internet could all be disrupted by a strong CME. The Carrington event remains the most powerful geomagnetic storm ever documented. Similar storms have struck Earth before, though with less intensity. If a storm of the same magnitude were to hit today, the consequences would be far more devastating. The modern world is built on electrical infrastructure, satellite communications, and digital networks, all of which could be crippled by a direct hit from a powerful CME. Scientists have developed ways to monitor and predict CMEs using spacecraft like the Solar and Heliospheric Observatory, or SOHO, and the Parker Solar Probe. These missions provide early warnings of incoming storms, allowing power companies and satellite operators to take precautions. Some power companies have begun reinforcing electrical grids with specialized transformers designed to withstand geomagnetic storms. But despite these efforts, there is little that can be done if a truly massive CME is directed towards Earth. In 2012, a massive CME erupted from the Sun with nearly the same strength as the 1859 storm. Fortunately, it missed Earth, passing through space just days after our planet had moved out of its path. Had it struck, it could have sent modern civilization into chaos. NASA scientists later confirmed that the storm could have caused trillions of dollars in damage, with recovery efforts taking years. Power grids would be among the first casualties of a storm of this scale. The electrical currents induced by a strong CME can overload transformers, causing them to overheat and fail. Unlike smaller outages, which can be restored by rerouting power, a geomagnetic superstorm could destroy key components, leading to blackouts that last for months. In 1989, a far weaker storm caused a power outage across Quebec, shutting down electricity for over 6 million people in less than 2 minutes. That storm was nothing compared to what a true Carrington-level event would do. High-energy particles from a major solar storm can interfere with or even destroy satellite electronics, knocking out GPS navigation, weather monitoring, and communications. Airlines rely on satellites for navigation, meaning a widespread failure could ground flights worldwide. Financial systems, which depend on precise time signals from satellites, could face massive disruptions, bringing global markets to a halt. Undersea internet cables, which carry data between continents, could also be affected. While fiber optic cables themselves are immune to solar storms, the electrical components that power them are not. A failure of these systems could cut off entire regions from the internet, making communication and coordination nearly impossible. The worst-case scenario would be a superflare, a CME far more powerful than anything recorded in modern history. Some stars in the galaxy have been observed producing superflares thousands of times stronger than anything the Sun has ever unleashed. If a similar event were to occur on our own Sun, the results would be catastrophic. A superflare would pose a direct threat to human health. High-energy particles from the storm would severely increase radiation levels, posing risks to most life on Earth. Food supply chains would be disrupted. Without communication networks, coordination for disaster response would be difficult. Water treatment facilities could fail, leading to shortages of clean drinking water. In the most extreme cases, the effects could last for decades, altering civilization as we know it. Scientists continue to study the Sun, hoping to understand when the next major CME might strike. But the reality is that these events are unpredictable. They can happen at any time with little warning, and once they begin, there is no way to stop them. The only question is whether Earth will be in their path when they arrive. The blinding fury of superflares from other stars. Astronomers have detected superflares on many types of stars, but they are most common on young, active stars that rotate rapidly. These stars have intense magnetic fields, which twist and snap with enormous force. When that energy is released, the result is a burst of radiation so powerful it can be seen from light years away. Some superflares eject more energy in a few hours than the Sun produces in an entire year. One of the most extreme examples came from a red dwarf star called AD Leonis. In 2008, astronomers observed it, releasing a flare hundreds of times more powerful than anything from the Sun. If Earth had been orbiting this star at the same distance it orbits the Sun, the atmosphere would have been stripped away instantly. Without its protective barrier, the planet's surface would have been bombarded with ultraviolet and X-ray radiation, killing anything exposed to the open sky. Red dwarfs are among the most common stars in the universe, and many of them host planets. Some of these worlds have been identified as potentially habitable, orbiting in just the right region where liquid water could exist. But their close proximity to their stars means they are exposed to constant bombardment from flares. Even if life did manage to emerge in such conditions, it would face an ongoing battle for survival. Superflares are not limited to small stars. Some of the most powerful have been observed on Sun-like stars, those that resemble our own in size and composition. A study of distant solar-type stars found that some of them produce superflares thousands of times stronger than anything recorded from the Sun. For most of its history, the Sun has been relatively stable. While it does release occasional strong flares, none have come close to the power of those seen on other stars. But there is no reason to believe the Sun is incapable of such an outburst. Studies of tree rings and ice cores suggest that Earth may have been hit by extreme solar storms in the distant past. One such event, known as the Miyake event, occurred around 774 AD. Evidence of an intense burst of radiation has been found in tree rings from that period, suggesting that the Sun may have unleashed a flare far stronger than anything in recorded history. Planets orbiting other stars have likely already experienced the full force of these cosmic explosions. Some may have once supported life, only to be rendered sterile by repeated radiation blasts. In extreme cases, superflares could even change the chemistry of a planet's atmosphere or trigger runaway greenhouse effects. The stellar vampires, stars that feed on their companions. Some stars are not content with the fuel they were born with. Instead of aging and dimming like their neighbors, they find a way to steal from others, extending their lives far beyond what should be possible. These are the stellar vampires, stars that feed on their companions to stay young and bright. Unlike normal stars, which follow a predictable path from birth to death, these cosmic outliers cheat their way into a second youth. Scientists call them blue stragglers, and first noticed them in star clusters, where stars are expected to be roughly the same age. Over time, these clusters evolve, and their most massive stars burn out and disappear. Yet, in many of these clusters, bright blue stars remain, far hotter and more luminous than they should be. Their existence defied explanation. These stars were old by all normal accounts, but they looked young. Many stars exist in binary systems, where two stars orbit one another, sometimes at extremely close distances. When one of these stars begins to expand into a red giant, its outer layers become weakly bound, allowing its smaller, more compact companion to pull material away. This slow process of siphoning transforms the thief into a blue straggler, a star that should have aged but has instead been reborn with fresh hydrogen fuel. As a star loses its outer layers, it becomes unstable. Some stripped stars collapse into white dwarfs, the dense, slowly cooling remnants of their former selves. Others may enter a period of erratic pulsation, releasing bursts of material before finally settling into a shrunken, depleted state. The more aggressive the theft, the more violent the consequences. In extreme cases, mass transfer can lead to a complete breakdown of the victim star, resulting in a supernova, a catastrophic explosion that leaves behind nothing but a rapidly expanding cloud of gas and dust. Not all blue stragglers form through theft. Some are created through direct collisions, particularly in densely packed star clusters. In these environments, stars move in tight, chaotic orbits, sometimes coming close enough to crash into one another. When two stars merge, their combined mass creates a new, larger star, which behaves like a young, hot sun, even though its components may be billions of years old. This violent method of formation explains why blue stragglers are often found in regions with high stellar densities, where close encounters between stars are common. Blue stragglers can shine with renewed intensity for millions of years, but their second youth is only temporary. As they burn through their newly acquired hydrogen, they eventually follow the same path as any other aging star. Some will expand into red giants, shedding layers of gas before shrinking into white dwarfs. Others, if massive enough, will end their lives in supernova explosions, leaving behind neutron stars or black holes. Despite their ability to delay the inevitable, they cannot avoid their fate forever. The feeding process of a stellar vampire can take place over millions of years. As a red giant expands, its gravitational pull weakens, allowing the smaller companion to gradually siphon gas away. This material spirals toward the thief star, creating a swirling disk of hot plasma that glows with intense radiation. Over time, the mass transfer accelerates, leading to dramatic changes in both stars. The thief gains mass and temperature, while the donor shrinks and loses its outer layers, exposing its hot core. In some cases, this process results in the formation of exotic objects, such as helium white dwarfs, stars that lost their outer envelopes before they had a chance to fully evolve. But there is another, even deadlier consequence of stellar vampirism. If the feeding star is a white dwarf rather than a normal star, the stolen material can accumulate on its surface until it reaches a critical threshold. At this point, a runaway nuclear reaction ignites, causing a thermonuclear explosion that obliterates the white dwarf in an instant. These explosions, known as Type Ia supernovae, are among the most powerful events in the universe. They release more energy in a single moment than the Sun will produce in its entire lifetime. These violent fates highlight the diversity in how stars evolve and interact. While some quietly burn through their fuel and fade away, others exist in a constant battle for survival, feeding on their neighbors or colliding in spectacular cosmic accidents. The existence of blue stragglers proves that the universe does not always follow simple rules. Sometimes stars can rewrite their own lifespans, taking what they need to shine a little longer. By observing blue stragglers in different environments, astronomers can piece together the violent history of star clusters and binary systems. They can track the fingerprints of mass transfer, the signs of ancient collisions, and the remnants of stars that were devoured by their companions. The doomsday impact of kilometer-wide asteroids. The Earth bears the scars of a violent past, marked by craters that tell the story of impacts stretching back billions of years. While most of these collisions happened in a distant time when the solar system was young and chaotic, asteroid impacts have never stopped. They are rare on human timescales, but in the vast timeline of planetary history, they are inevitable. The asteroid that ended the reign of the dinosaurs was not the first, nor will it be the last. When a kilometer-wide asteroid strikes a planet, it unleashes energy equivalent to millions of nuclear bombs detonating at once. The impact generates a shockwave that flattens everything for hundreds of kilometers. The heat from the explosion ignites wildfires on a massive scale. If the asteroid strikes the ocean, it displaces so much water that tsunamis taller than skyscrapers race across the planet. The after effects can last for decades or even centuries, plunging the world into a temporary darkness that disrupts climate, food chains, and civilizations. The Chicxulub impact, which brought an end to the dinosaurs 66 million years ago, was one of the most devastating in Earth's history. The asteroid, estimated to be around 10 to 15 kilometers across, struck what is now Mexico's Yucatan Peninsula. The explosion carved out a crater over 180 kilometers wide and sent debris hurtling into the atmosphere. The shockwave alone would have been enough to wipe out everything nearby, but the real devastation came from what followed. The intense heat ignited global wildfires, while the dust and soot blocked out sunlight, triggering a dramatic cooling period known as an impact winter. Plants withered, food chains collapsed, and 3/4 of all species on Earth vanished. The Redefort crater in South Africa, estimated to be over 2 billion years old, is the largest confirmed impact structure on the planet. The asteroid responsible may have been over 20 kilometers wide, striking with such force that it deformed Earth's crust. Another famous impact site, the Sudbury Basin in Canada, is nearly as ancient, dating back 1.8 billion years. The object that created it is thought to have been around 10 kilometers in diameter, comparable in size to the Chicxulub impactor. Unlike earthquakes or hurricanes, asteroid impacts do not follow seasonal patterns or fault lines. They come from deep space, unpredictable and indifferent to the civilizations that stand in their path. The best way to prevent a catastrophe is to spot these objects early before they have a chance to strike. Telescopes on Earth and in space are constantly scanning the skies for near-Earth objects, asteroids and comets that pass close to our planet. NASA's Near-Earth Object Observations program, along with international efforts, tracks thousands of these objects, mapping their orbits and projecting their future paths. Most asteroids in the solar system reside in the main asteroid belt between Mars and Jupiter, where they orbit harmlessly. However, gravitational interactions can nudge them out of stable paths, sending them toward Earth-crossing trajectories. Some of the most concerning asteroids belong to the Apollo and Aten groups, populations of space rocks whose orbits bring them dangerously close to our planet. While most pass by harmlessly, even a small miscalculation in their path could mean disaster. Several known asteroids have raised alarms in recent years. Apophis, a 370-meter-wide asteroid, was once thought to pose a significant risk of impact in the 21st century. Early calculations suggested it had a chance of colliding with Earth in 2029 or 2036, but refined measurements ruled out an impact, at least for the near future. Another object, Bennu, is about 500 meters across and has a slight chance of hitting Earth in the late 2100s. While these asteroids are not large enough to cause mass extinctions, they could still devastate entire regions, flattening cities and altering weather patterns on a global scale. If an asteroid were discovered on a collision course with Earth, the world's only option would be to deflect or destroy it before impact. The longer the warning time, the better the chance of success. One proposed method is the kinetic impactor, a spacecraft designed to slam into an asteroid at high speed, nudging it slightly off course. NASA's Double Asteroid Redirection Test, or DART mission, was the first real-world test of this concept. In 2022, the DART spacecraft deliberately crashed into Dimorphos, a small asteroid orbiting a larger body named Didymos. The impact successfully altered the asteroid's trajectory, proving that such a technique could work if ever needed. Other deflection ideas include gravity tractors, in which a spacecraft flies alongside an asteroid, using its small gravitational pull to slowly change the asteroid's path. More extreme solutions involve nuclear explosions, not to destroy the asteroid, but to push it onto a different course. However, this approach carries risks, as breaking an asteroid apart could create multiple dangerous fragments instead of a single large impact. Despite ongoing efforts to detect and track hazardous asteroids, there are still blind spots. Some asteroids approach from the direction of the Sun, making them difficult to see until they are alarmingly close. In 2013, a 20-meter-wide asteroid exploded over Chelyabinsk, Russia, with the force of about 30 Hiroshima bombs. The explosion shattered windows across the city and injured over 1,500 people, yet no one saw it coming. The asteroid had approached from the daylight side of Earth, evading detection entirely. Even larger objects could remain hidden until it is too late. In 2019, an asteroid nearly 100 meters across passed just 70,000 kilometers from Earth, about one-fifth the distance to the Moon. It was only spotted a day before its closest approach. Events like these highlight the need for more advanced detection systems, including space-based telescopes that can spot asteroids approaching from the Sun's direction. While the odds of a major impact in any given year are low, the consequences of even a single collision are so severe that the risk cannot be ignored. Unlike other natural disasters, asteroid impacts are preventable, but only if they are detected early enough for action to be taken. Governments and space agencies around the world continue to refine strategies for planetary defense, knowing that one day the fate of humanity may depend on it. The craters on the Moon, Mars, and Earth itself serve as a stark reminder that space is not empty, and that hidden among the darkness, countless objects continue their silent journey, some of them, perhaps, aimed directly at us. Cosmic cannibalism. Galaxies that devour their neighbors. Galaxies exist in a vast cosmic web interacting with one another over millions and billions of years. The universe is filled with galactic collisions, a process in which larger galaxies consume smaller ones, distorting their shapes and incorporating their stars, gas, and dust. This process, known as galactic cannibalism, has been a driving force in the evolution of the cosmos since its earliest days. Some galaxies merge peacefully, gradually blending together over time. Others engage in violent encounters, ripping each other apart in dramatic displays of gravitational destruction. The Milky Way itself is no stranger to this process. It has absorbed multiple smaller galaxies throughout its history and continues to do so today. One of the best examples is the Sagittarius Dwarf Galaxy, a small elongated system that is slowly being torn apart by the Milky Way's gravity. Its stars are being stripped and scattered, forming streams that wrap around our galaxy. This is not the first time the Milky Way has consumed a companion, and it will not be the last. Some of the most extreme cases of galactic cannibalism involve massive elliptical galaxies in the centers of galaxy clusters. These giants, known as brightest cluster galaxies, have devoured numerous smaller systems over billions of years, growing into enormous bloated structures. One such example is IC 1101, one of the largest galaxies ever discovered. Located over 1 billion light-years away, it stretches more than 6 million light-years across, dwarfing the Milky Way. It has likely swallowed hundreds of smaller galaxies in its lifetime, growing to its immense size through relentless mergers. The Andromeda Galaxy, our closest large neighbor, is also an active participant in cosmic cannibalism. It continues to absorb new systems, and in a few billion years, it will set its sights on an even bigger target, the Milky Way. Andromeda and the Milky Way are on a collision course, moving toward each other at a speed of about 110 kilometers per second. In roughly 4.5 billion years, the two galaxies will collide in a dramatic event that will reshape both systems. Unlike smaller mergers, which are often one-sided affairs, this will be a true galactic-scale collision. The sheer scale of each galaxy means that individual stars are unlikely to collide, as the distances between them are vast. However, the immense gravitational forces will send stars on chaotic new paths, distorting the galaxies into long tidal tails before they eventually settle into a new, merged structure. Simulations suggest that the final product of this collision will be a giant elliptical galaxy, sometimes referred to as Milkomeda. The spiral arms of both galaxies will be disrupted, their central regions blending together as they form a single, massive structure. The supermassive black holes at the centers of both galaxies will also interact, gradually spiraling toward each other before merging in a powerful event that will send gravitational waves rippling through the universe. Beyond our own local environment, galactic collisions play a crucial role in shaping the universe. One of the most extreme examples of a violent merger is the antennae galaxies, a pair of interacting galaxies locked in a dramatic collision. Their elongated, curved arms stretch out like antennae, the result of immense tidal forces pulling them apart. These galaxies are in the process of fully merging, triggering bursts of star formation as clouds of gas collide and collapse under gravity. The energy of this encounter will eventually settle into a new, singular galaxy. In some cases, galactic cannibalism can lead to the complete destruction of smaller galaxies. The Tadpole Galaxy, located over 400 million light-years away, is an example of a galaxy in the process of being torn apart. A smaller galaxy is currently being absorbed, leaving behind a long tail of stars stretching out for hundreds of thousands of light-years. Eventually, this smaller galaxy will be completely integrated, its stars becoming part of the Tadpole Galaxy's structure. While most galactic mergers involve gravitational forces alone, some interactions can trigger extreme energetic events. When gas-rich galaxies collide, the influx of material into their centers can feed their supermassive black holes, igniting them as quasars. These powerful objects unleash intense radiation, sometimes outshining entire galaxies. In some cases, mergers can lead to active galactic nuclei, regions where black holes consume vast amounts of matter, driving high-energy jets that shoot across space. Star formation often surges in colliding galaxies as gas clouds are compressed, leading to the birth of new stars. The Milky Way's own history of minor mergers may have helped shape its structure, influencing the formation of its spiral arms and central bulge. Looking forward billions of years, the fate of our galaxy is clear. The Milky Way, Andromeda, and their smaller neighbors will eventually merge into a single massive system. By that time, the Sun will likely be nearing the end of its life, slowly evolving into a red giant before fading away. Humanity, if it still exists, may witness the birth of a new elliptical galaxy, formed from the remnants of the structures that once made up the local group. The night sky, which seems so still on human timescales, is actually a place of constant motion. Galaxies drift through space, drawn together by gravity, locked in a cosmic dance that plays out over millions and billions of years. The stars that seem so permanent will eventually merge, transform, and begin a new chapter in the vast history of the cosmos. The chaotic dance of three-body systems. The motion of celestial bodies is often predictable when only two objects are involved. A single planet orbits a star in a stable path, its movement governed by simple gravitational rules. But when a third massive object enters the picture, things become much more complicated. The introduction of another gravitational force disrupts the balance, creating a system where movement is no longer predictable over long periods. This is the infamous three-body problem, one of the most challenging puzzles in physics. Three-body systems can form in many ways. Some begin as binary star systems, where two stars orbit each other in a stable pattern, only for a third massive object, a planet, another star, or even a black hole, to arrive and disrupt their motion. Others arise naturally in dense star clusters, where gravitational interactions frequently pull celestial objects into unstable configurations. Over time, these systems evolve unpredictably, with their members being tossed around by competing gravitational influences. One of the most extreme outcomes of an unstable three-body system is the ejection of a planet into interstellar space. When a planet orbits two stars, its gravitational environment is already complex, as it must navigate the shifting pull of both stellar masses. If a third massive body, such as another planet or an additional star, is introduced into the mix, the system can quickly become unstable. The competing forces push and pull on the planet unpredictably, altering its orbit in ways that can eventually send it flying out of the system at tremendous speeds. Once a planet is ejected, it becomes a rogue world, drifting through the galaxy without a host star, condemned to eternal darkness unless it encounters another system that captures it. In multi-star systems, planets often have highly eccentric orbits, elongated and stretched due to past gravitational disruptions. Some exoplanets have been discovered with orbits so extreme that they seem to be on the verge of being thrown out of their systems entirely. Others may have already been lost, flung into the depths of space long before they could be detected. But ejection is not the only fate that can await a planet in a three-body system. If a planet is caught in an unstable orbit due to the influence of a third body, its path can decay over time. Small changes in its trajectory, amplified by the complex gravitational interactions at play, can send it closer and closer to its parent star. Eventually, tidal forces and atmospheric drag can accelerate its inward spiral, leading to an eventual collision with the star itself. In star clusters, where many stars exist in close proximity, three-body encounters are common. When three stars interact, one can be ejected while the remaining two form a stable binary pair. This process plays a crucial role in shaping the evolution of star clusters, determining which stars stay and which are flung away into interstellar space. Some of the fastest-moving stars in the galaxy, known as hypervelocity stars, are thought to have been ejected from their original homes due to such interactions, sent speeding through the Milky Way at thousands of kilometers per second. Even black holes are not immune to the chaos of three-body dynamics. In dense galactic centers, where supermassive black holes lurk, smaller black holes and neutron stars can be thrown around by the intense gravitational environment. Some may be flung into intergalactic space, while others may be forced into orbits that bring them closer and closer to the central black hole, eventually leading to their destruction. In some cases, these interactions can lead to gravitational wave events, where black holes or neutron stars collide and send ripples through space-time. The unpredictable nature of three-body systems is one of the reasons why long-term planetary stability is so difficult to guarantee. Even a seemingly stable system can be thrown into chaos if an unexpected disturbance occurs. A passing star, a wandering rogue planet, or even a distant gravitational influence from another system can trigger a cascade of interactions that reshuffle the orbits of planets, moons, or even entire star systems. Over millions of years, the effects of these disruptions build up, changing the architecture of planetary systems in ways that are impossible to predict with complete accuracy. In some cases, three-body interactions can create unusual planetary configurations. Some exoplanets have been found in orbits that seem impossible at first glance, highly elongated paths that take them close to their stars before flinging them far away into deep space. Others are trapped in resonances, where their movement is locked into a repeating cycle due to the gravitational influence of multiple bodies. Supercomputers are used to model how three or more objects interact over time, revealing the possible outcomes of these chaotic dances. While the exact paths of individual objects may be impossible to predict over long periods, statistical patterns can emerge, helping scientists understand the likelihood of different scenarios. The universe is shaped by gravity, but in many cases, gravity does not create order, it creates chaos. The forces that govern the motion of celestial objects can lead to destruction just as easily as they lead to creation. The chaotic dance of three-body systems is an ongoing cosmic performance, one that continues to shape the structure of the universe in unpredictable ways. The relentless approach of the Oort cloud's hidden killers. At the farthest reaches of our solar system, beyond the orbits of the planets, beyond even the icy debris of the Kuiper belt, lies a distant and largely invisible shell of frozen objects, the Oort cloud. It is a vast, mysterious reservoir of comets, stretching perhaps a light-year from the Sun. These frozen wanderers have remained undisturbed for billions of years, but they are not always safe from disruption. The Oort cloud is a ticking time bomb, and all it takes is one passing star to send a deadly swarm of comets hurtling toward the inner solar system. Scientists believe the Oort cloud contains trillions of icy bodies, leftovers from the early formation of the solar system. Unlike the more well-known asteroid belt or Kuiper belt, the Oort cloud is not a flat disk. Instead, it forms a spherical shell, a diffuse frozen halo surrounding the Sun. Objects out there are so distant that they barely feel the Sun's gravitational pull. A gentle nudge could dislodge them, sending them tumbling inward. Some may spiral toward the Sun harmlessly, but others may cross Earth's path, becoming long-period comets, capable of striking the planet with devastating force. This has likely happened before. The Chicxulub impact is believed by some scientists to have been caused by a long-period comet. While most studies point to an asteroid as the culprit, there is growing evidence that at least some of Earth's mass extinctions were triggered by comet impacts. These objects travel much faster than asteroids, making their collisions with Earth even more violent. A comet several kilometers wide could release energy equivalent to billions of atomic bombs, igniting wildfires, triggering tsunamis, and shrouding the planet in darkness. Astronomers have identified past and future encounters between the Sun and other stars that could disrupt the Oort cloud. One of the most significant of these was caused by a star named Scholz's star, which passed within less than a light-year of the Sun about 70,000 years ago. At the time, early humans were already spread across the planet, unaware that a distant star was subtly altering the solar system's outermost reaches. If it sent any comets inward, their arrival would still be thousands of years away, as these objects take immense periods of time to reach the inner solar system. A future encounter may have even more dramatic consequences. In about 1.3 million years, a star named Blitzar 710 is expected to pass through the Oort cloud itself, coming within just 0.06 light-years of the Sun. That is closer than any known star has come in recorded history. At that distance, its gravitational pull could send thousands, perhaps even millions of Oort cloud objects tumbling toward the inner solar system. Most would miss Earth, but a small fraction could become dangerous. If even a handful were large enough to survive the journey intact, they could pose an existential threat to life on our planet. Unlike near-Earth asteroids, which can be tracked for years or even decades before they become a threat, these comets often arrive with little warning. Their orbits are highly elongated, meaning they spend most of their existence in darkness, invisible to telescopes. Only when they approach the inner solar system and begin to warm up do they develop their characteristic glowing tails, making them easier to detect. But by that time, it may be too late. A large comet on a collision course with Earth could become visible only months before impact, leaving little time for preparation or deflection. There have already been near misses. In 1996, a comet named Hyakutake appeared seemingly out of nowhere, passing within 15 million kilometers of Earth, just 40 times the distance to the Moon. It had been completely undetected until a few months before its closest approach. Even more alarming was Comet C2013A1, which came within 140,000 kilometers of Mars in 2014. That is less than half the distance between Earth and the Moon. If such a comet were headed for Earth, there would be almost no time to react. Some astronomers have suggested that a future space telescope stationed far beyond the orbit of Neptune could be used to detect incoming long-period comets before they reach the inner solar system. But for now, Earth's best defense remains luck, hoping that no unseen comet is currently hurtling toward us on an invisible trajectory. A few scientists believe that the Sun's movement through the Milky Way occasionally brings it into regions of higher stellar density, increasing the chances of an Oort cloud disturbance. If this happens at regular intervals, it could explain why Earth has experienced extinction cycles roughly every 26 million years. Though this idea remains controversial, it highlights just how fragile life can be in the face of cosmic events far beyond human control. Hypernovae, supernovae's bigger, deadlier cousin. A supernova is one of the most powerful explosions in the universe, capable of outshining entire galaxies for a short period. But there is something even more extreme. When the most massive stars in the cosmos reach the end of their lives, they don't just explode, they collapse with such force that they trigger an event more violent than a supernova. This is a hypernova, a cosmic explosion so powerful that it releases 10 times more energy than a standard supernova, sending deadly radiation and high-speed particles across vast distances. Hypernovae happen when stars with at least 30 to 50 times the mass of the Sun reach the end of their lifetimes. These stars burn through their nuclear fuel much faster than smaller ones, fusing lighter elements into heavier ones until they can no longer support their immense weight. In a regular supernova, this collapse creates a neutron star or, in some cases, a black hole. But in a hypernova, the sheer mass of the star allows it to collapse in an even more dramatic fashion. The core implodes with such intensity that it tears through its outer layers, launching enormous shockwaves that rip apart the star in a fraction of a second. The explosion releases as much energy as millions or even billions of suns shining at once. Gamma rays are the highest energy form of light, invisible to human eyes, but incredibly dangerous. When a hypernova occurs, it can create twin beams of gamma rays that shoot out from the collapsing core at nearly the speed of light. These beams can travel across the universe, slicing through anything in their path. If Earth were in the direct line of fire from such an event, the consequences could be devastating. The upper atmosphere would absorb the gamma radiation, triggering a chain reaction that could strip away the ozone layer. With the planet suddenly exposed to harsh ultraviolet radiation from the Sun, life on the surface would be in grave danger. Hypernovae have already been detected in other galaxies, but they are rare. The most famous example is GRB 980425, a gamma-ray burst that was linked to a hypernova called SN 1998 BW. This explosion occurred in a galaxy about 120 million light-years away. Another, GRB 030329, came from an even more extreme hypernova, located roughly 2.6 billion light-years from Earth. The sheer distance of these events meant that their radiation had no impact on our planet, but they provided a glimpse into just how violent hypernova can be. Scientists estimate that for a gamma-ray burst to significantly affect life on Earth, it would need to occur within 5,000 to 8,000 light-years. While this might seem like a safe distance, the Milky Way is filled with massive stars, and some are certainly capable of ending their lives in hypernovae. One of the biggest concerns is WR104, a massive star system located about 8,100 light-years from Earth. WR104 consists of two stars locked in a tight orbit, with the larger one being a Wolf-Rayet star, a type of star nearing the end of its life. Wolf-Rayet stars are some of the most likely candidates to explode in hypernovae. The concern with WR104 is that its axis of rotation appears to be pointed in our general direction. If it were to collapse in a hypernova and produce a gamma-ray burst, there is a possibility that Earth could be within the danger zone. Another potential candidate is Eta Carinae, a massive and unstable star system about 7,500 light-years away. Eta Carinae has already shown signs of extreme instability, having undergone a massive outburst in the 19th century known as the Great Eruption. This event was so bright that for a time, Eta Carinae became the second brightest star in the night sky. Since then, it has calmed down, but astronomers believe it is still on a path towards an explosive end. Unlike WR104, Eta Carinae's exact orientation remains uncertain, but if it were to produce a gamma-ray burst, its distance places it dangerously close to the range where Earth could experience severe effects. Even if a hypernova doesn't directly hit Earth with a gamma-ray burst, it could still pose a serious threat. The explosion would release vast amounts of high-energy cosmic rays. If a hypernova occurred within a few thousand light-years, these particles could eventually reach Earth, causing long-term damage to the atmosphere and increasing radiation levels on the surface. Some scientists believe past extinction events may have been triggered by supernovae or hypernovae that bathed Earth in cosmic radiation, weakening the planet's protective layers and exposing life to dangerous conditions. Despite the dangers, hypernova are a fundamental part of the universe's life cycle. They play a crucial role in spreading heavy elements across space, seeding new star systems and planets with the raw materials needed for life. Without these explosions, elements like gold, uranium, and platinum would be far less common. Even the iron in human blood likely originated from a long-dead massive star that exploded billions of years ago. In a way, hypernovae are both destroyers and creators, shaping the evolution of galaxies and the very fabric of the cosmos. Quark stars, theoretical monsters that shouldn't exist. Quark stars are a theoretical type of compact object that could exist somewhere between neutron stars and black holes. While no quark stars have been confirmed, some scientists believe they may form under extreme conditions, where the pressure inside a collapsing star is so immense that even neutrons themselves break apart. Instead of being made of individual neutrons packed together like in a neutron star, a quark star would contain a soup of their fundamental building blocks, quarks. These stars would be unimaginably dense, possibly reaching a state where matter exists in a form unlike anything seen elsewhere in the universe. Neutron stars form when a massive star runs out of fuel and collapses under its own gravity. The outer layers of the star explode outward in a supernova, while the core is compressed so tightly that protons and electrons merge to create neutrons. The result is a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. But if the collapsing core of a star is massive enough, it might go even further, crushing the neutrons themselves and creating a sea of free quarks, the particles that make up protons and neutrons. The matter inside a quark star would exist in a state known as strange quark matter, a theorized form of matter containing not just the usual up and down quarks found in ordinary matter, but also strange quarks. If such a state of matter is stable, it could mean that quark stars could exist without immediately collapsing into black holes. Some theories suggest that quark stars might be slightly smaller and denser than neutron stars, but with properties that make them unique. Their surface might be smoother, their magnetic fields even stronger, and their ability to emit radiation potentially different from other compact objects. Detecting a quark star would be incredibly difficult, as, to an outside observer, it could look almost identical to a neutron star. Both would be small, dense, and capable of emitting powerful X-rays and radio waves. However, there are a few possible clues that could reveal their existence. One idea is that quark stars might have different cooling rates compared to neutron stars. The way they release heat could provide a signature that astronomers could look for. Some neutron stars that appear to be cooling faster than expected have been suggested as possible quark star candidates. If quark stars exist, they could have some unsettling properties. One of the more unusual and potentially dangerous ideas surrounding them is that strange quark matter could be contagious. This theory suggests that if strange quark matter is more stable than ordinary matter, then anything it comes into contact with could be transformed into the same exotic state. This raises the alarming possibility that if a quark star ever collided with a neutron star or another celestial body, it might trigger a chain reaction, converting normal matter into strange quark matter in the process. If this were to happen, it could have catastrophic consequences, destroying entire stellar systems in the process. Collisions involving quark stars would be some of the most violent events in the universe. When two neutron stars merge, they release an enormous amount of energy in the form of gravitational waves and gamma-ray bursts. If at least one of those stars was a quark star, the resulting collision could create an unstable object that quickly collapses into a black hole, or alternatively, form a new quark star that is even larger and more energetic than before. Experiments on Earth, such as those conducted at particle accelerators like the Large Hadron Collider, can recreate some of the conditions that existed in the early universe, where quarks were free rather than bound inside protons and neutrons. However, there is still much to learn about whether quark matter can be stable over long periods. If it turns out that quark stars can exist, it would mean that there is an entirely new category of stellar remnants beyond what is currently known. Another possibility is that some black holes may have originally formed as quark stars, before collapsing entirely under their own gravity. If this is the case, then quark stars may be a brief but significant stage in the life cycle of extremely massive stars. If a true quark star is ever discovered, it could change what is known about the fundamental nature of matter and provide new insights into the evolution of stars and black holes. Until then, they remain one of the most intriguing and elusive possibilities in astrophysics, straddling the line between the known and the unknown. Magnetars, the most extreme magnetic fields in the universe. Magnetars are dense, dead stars that possess magnetic fields so powerful they defy human comprehension. If a magnetar were as close as the Moon, its intense magnetic forces would erase the data on every credit card and hard drive on Earth. But even from light years away, these celestial monsters can unleash bursts of energy strong enough to shake the very fabric of space. A magnetar begins its life as a massive star, far larger than the Sun. When it reaches the end of its life cycle, it explodes in a violent supernova, collapsing its core into an unimaginably dense neutron star. But unlike ordinary neutron stars, some of these remnants are born with an extraordinary trait, a magnetic field trillions of times stronger than anything else known. While a typical neutron star already has an intense magnetic field, a magnetar takes this to an entirely different level, with forces up to a quadrillion times stronger than Earth's. These magnetic fields are so extreme that they stretch and distort the very atoms that make up matter. If an object were to drift too close, the intense forces would pull it apart at the atomic level, reducing it to a plasma of scattered particles before it even had a chance to collide with the star itself. This effect is so powerful that if a human were somehow able to survive near a magnetar, their very molecules would be torn apart. But magnetars are not just strange because of their magnetism. They are also some of the most violent objects in the cosmos. Unlike other neutron stars, which tend to be relatively stable, magnetars experience constant turmoil. Their powerful magnetic fields twist and shift, generating immense pressure beneath the surface. When the strain becomes too great, the crust of the star cracks open in what is essentially a starquake. These violent events release enormous amounts of energy, sending powerful blasts of X-rays and gamma rays across the universe. Some of the most intense flashes of radiation ever recorded have come from magnetars, and astronomers believe they may occasionally produce bursts powerful enough to affect planets many light years away. One such event occurred in 2004 when a magnetar located 50,000 light-years from Earth suddenly erupted in an enormous gamma-ray burst. The blast was so powerful that it briefly altered Earth's ionosphere, affecting radio communication. This was despite the fact that the magnetar was located on the other side of the galaxy. Had it been closer, the results could have been far more severe. Some of them appear to emit bursts of radio waves similar to fast radio bursts, or FRBs, mysterious high-energy pulses that have puzzled astronomers for years. If magnetars are indeed the source of FRBs, it would suggest they are even more unpredictable than previously thought. Despite their terrifying power, magnetars are incredibly rare. Only about 30 have been identified in our galaxy, though many more likely exist. Their lifespans are also short by cosmic standards. Within a few million years, an instant in astronomical time, their magnetic fields weaken and they settle into being ordinary neutron stars. Magnetars are the ultimate demonstration of what happens when the laws of physics are pushed to their limits. Whether through powerful bursts of radiation or their ability to stretch atoms apart, they stand as some of the most formidable forces nature has ever produced. False vacuum decay, the universe's self-destruct button. The universe appears to be vast, stable, and unchanging on the grandest scales. The stars have burned for billions of years. Galaxies have collided and reformed over cosmic time, and the fundamental forces of nature have remained the same since the birth of existence. But what if this stability is an illusion? What if the very foundation of reality, the vacuum of space itself, is a ticking time bomb? One that could detonate without warning and erase everything in an instant. This is the terrifying possibility of false vacuum decay, a hypothetical event that would not just destroy Earth or the galaxy, but rewrite the very fabric of physics itself. In physics, the vacuum is not simply empty space. It is the lowest energy state of the universe, the baseline level from which everything else exists. But what if this vacuum is not actually the lowest possible state? What if it is what scientists call a false vacuum, a temporary, unstable condition that only appears stable because it hasn't yet been disturbed? In this scenario, there is a deeper, more stable vacuum state, but transitioning to it would unleash an unimaginable catastrophe. The best way to picture this is to imagine a ball resting in a shallow valley on a landscape of rolling hills and deeper valleys. The ball appears stable where it is, but if a small nudge were to push it over the edge, it would roll down into a much deeper valley where it would be even more stable. The problem is that this fall would release an enormous amount of energy, and if this were to happen to the vacuum of space itself, the consequences would be universe-shattering. If a false vacuum were to decay into a true vacuum, it would do so by creating a bubble of the new lower energy state. This bubble would expand outward at the speed of light, obliterating everything in its path. Unlike supernovae, black holes, or even gamma-ray bursts, which are localized events, this would be an all-encompassing wave of destruction that sweeps through the universe with no way to stop it. Within this bubble, the fundamental forces of nature could be completely rewritten. The very structure of atoms might change. The laws governing electromagnetism, gravity, and nuclear forces could shift in ways that render all matter unrecognizable. Chemistry as we know it might cease to function, and planets, stars, and life itself would be instantly destroyed or altered beyond comprehension. This wouldn't just be the death of Earth or the Milky Way. It would be the end of the universe as we understand it. One of the most terrifying aspects of false vacuum decay is that there would be no warning. Because the destruction travels at the speed of light, we would not see it coming. There would be no incoming explosion, no distant flash of energy to alert us to the end. One moment, the universe would exist as it always has. The next, reality itself would be erased. But how likely is this to happen? The unsettling answer is that we don't really know. According to some interpretations of particle physics, the universe may indeed be in a metastable state, meaning that it is not truly stable but also not unstable enough for decay to happen anytime soon. The behavior of the Higgs boson, a fundamental particle discovered in 2012, suggests that we may be living in a universe that is only temporarily stable. If this is true, then vacuum decay is not just possible, it is inevitable. However, the timescales involved may be reassuringly vast. If vacuum decay were possible, calculations suggest that it might take trillions upon trillions of years before a random quantum fluctuation triggers the process. This means it is extremely unlikely to happen within the lifetime of the Sun, the Milky Way, or even the observable universe as we know it. But what could trigger such a transition? One possibility is a random quantum fluctuation, a tiny shift in energy at the subatomic level that happens spontaneously due to the laws of quantum mechanics. If such a fluctuation were to occur in just the right way, it could act as the push that starts the vacuum collapse. Another possible trigger is an incredibly high energy event, such as a collision between cosmic rays. Some physicists have even speculated that advanced civilizations, if they ever achieved the ability to manipulate energy at unimaginable scales, could accidentally trigger vacuum decay by conducting experiments with extreme forces. Some argue that if vacuum decay were a real threat, it likely would have already happened. The universe has existed for 13.8 billion years, and during that time it has undergone countless extreme events: black hole formations, collisions between neutron stars, and unimaginable cosmic explosions. If any of these events were capable of triggering vacuum decay, it should have already occurred, wiping out everything long before humans ever came into existence. The fact that we are still here suggests that either the vacuum of space is truly stable, or the timescale for vacuum decay is so long that it becomes a theoretical rather than practical concern. Experiments at various particle physics research centers have studied vacuum stability by examining the behavior of particles like the Higgs boson. So far, there is no evidence that we are on the brink of vacuum decay, but the possibility remains open. Theoretical physics has not ruled it out, and in a universe governed by quantum mechanics, anything that is possible, no matter how unlikely, can eventually happen given enough time. Unlike asteroid impacts, supernova explosions, or even black hole encounters, which humanity might one day develop defenses against, vacuum decay is an existential event that offers no chance for survival. Despite its terrifying implications, vacuum decay remains largely a theoretical concern. The fact that the universe has survived for billions of years suggests that even if it is not in a perfectly stable state, it is stable enough that the risk of sudden annihilation is so small that it might as well not exist. Even if vacuum decay were possible, it could take longer than the current age of the universe by an incomprehensible margin before such an event would ever occur. For now, we can take comfort in the fact that the universe appears stable, at least on the scales that matter to us. But the possibility of false vacuum decay serves as a humbling reminder that even the most fundamental aspects of existence are not necessarily permanent. Helium flash, the explosive death throes of certain stars. Even the most stable and long-lived stars eventually run out of fuel and begin their slow decline toward death. For Sun-like stars, this process unfolds over billions of years, with the star gradually expanding into a red giant as it exhausts its hydrogen supply. But hidden within this seemingly gentle transformation is a sudden and violent event known as a helium flash. This is not the catastrophic supernova of a massive star, but rather an internal explosion, one that ignites deep within the core of the dying star, releasing an enormous burst of energy in an instant. Though largely hidden from view, helium flashes are among the most extreme transformations a low-mass star can experience. The helium flash occurs in stars with masses between about 0.8 and 2.3 times that of the Sun, stars that are too small to end their lives in supernova, but large enough to go through an extended red giant phase. The process begins after the star has burned through most of its hydrogen fuel. At this stage, the outer layers of the star expand dramatically, while the core, now composed mostly of helium, contracts under the force of gravity. This helium core becomes so dense that its atoms are squeezed into a state known as electron degeneracy. In normal stellar conditions, increasing temperature causes atoms to move faster, allowing the pressure to regulate itself. But in a degenerate core, pressure is governed by quantum mechanical rules rather than temperature. This means that even as the core gets hotter, its pressure remains largely unchanged. As more helium accumulates in the core, the temperature continues to rise, creeping toward the critical threshold where helium fusion can begin. In an ordinary situation, fusion starts gradually, allowing the star to adjust as it begins burning helium into heavier elements like carbon and oxygen. But in a degenerate core, there is no such balance. Since the pressure is not responding to temperature, there is nothing to slow the reaction once it starts. When the core reaches around 100 million degrees Kelvin, helium fusion ignites in a runaway process. In just a few seconds, an enormous amount of energy is released, comparable to the entire output of a galaxy. Despite the immense energy involved, the helium flash does not tear the star apart or create a visible explosion in space. This is because the outer layers of the red giant act as an insulating shell, absorbing the burst of energy and gradually redistributing it throughout the star. The result is a dramatic change in the star's structure. The core rapidly expands, reducing its density and cooling it down. This expansion stops the runaway fusion from continuing and allows the star to settle into a new phase of stable helium burning. In a sense, the helium flash is like a hidden detonation, one that reshapes the star from within, but does not destroy it. For most Sun-like stars, the helium flash is a relatively contained event, but in more extreme conditions, it can become even more violent. One scenario where this happens is in stars that undergo repeated helium flashes late in their lives. These stars, known as thermal pulsing asymptotic giant branch stars, experience cycles of helium shell flashes that cause them to periodically brighten and expel large amounts of their outer layers into space. Over time, this shedding of mass contributes to the formation of a planetary nebula, the glowing shell of gas left behind when a star like the Sun reaches the final stage of its life. In some rare cases, a helium flash may not occur inside a star at all, but instead on the surface of a dead stellar remnant. This can happen in a binary system where a white dwarf, an Earth-sized remnant of a dead Sun-like star, steals helium-rich material from a companion. If enough helium accumulates on the surface of the white dwarf, it can ignite in a flash similar to what occurs in a red giant's core. These events, sometimes called helium novae, cause sudden bursts of brightness as the white dwarf temporarily flares up before settling down again. If a white dwarf accumulates enough helium under the right conditions, the helium flash could trigger a full-scale thermonuclear explosion, disrupting the star in an event known as a Type Ia supernova. While most helium flashes occur inside red giants and remain hidden from view, there is growing evidence that in some cases, these events might become visible to distant observers. Some astronomers believe that certain luminous outbursts seen in space, such as the sudden brightening of otherwise unremarkable stars, could be linked to helium ignition under unusual conditions. Based on current models, the Sun is expected to go through a helium flash in about 5 billion years, after it has expanded into a red giant. However, since the Sun is on the lower end of the mass range for helium flashes, its explosion will likely be less dramatic than those in heavier stars. It will still mark a turning point in the Sun's life, signaling its transition into the final stages of stellar evolution. Strange matter. Could a single particle destroy the Earth? In the world of theoretical physics, some of the most terrifying ideas come from the very building blocks of matter itself. One such idea is the existence of strange matter, an exotic form of matter so stable that if it ever came into contact with ordinary atoms, it could trigger a chain reaction that transforms everything it touches. Some physicists have speculated that if even a single strangelet, a tiny but powerful fragment of this hypothetical substance, were to reach Earth, it could convert the entire planet into a lifeless lump of strange matter. All known matter in the universe is composed of quarks, which come in 6 types: up, down, strange, charm, top, and bottom. Ordinary matter is made up of only up and down quarks. However, under extreme conditions, such as the immense pressure found inside neutron stars, some physicists believe that quarks can rearrange themselves into a new, more stable configuration that includes strange quarks. The result would be a substance called strange matter, which could be denser, more stable, and potentially longer lasting than any form of normal matter. If strange matter is truly the most stable form of matter, then any ordinary atoms that come into contact with it might be forced into the same state. In other words, normal atomic nuclei would be converted into more strange matter, setting off a chain reaction. This process could, in theory, spread through an entire planet, star, or even an entire galaxy, transforming all matter into a uniform mass of strange matter. The idea of a planet consuming strangelet was first seriously discussed in the late 20th century, when scientists studying high-energy physics realized that such objects might be created naturally in the universe. Some theories suggest that neutron stars might actually transform into strange stars. If these strange stars exist, they could occasionally shed tiny fragments of themselves, launching strangelets into space. One of the biggest uncertainties is whether strange matter is truly more stable than ordinary atomic matter. If it is not, then strangelets would likely be short-lived and incapable of triggering a chain reaction. If, however, strange matter is even slightly more stable than normal matter, then the possibility of a strangelet-induced catastrophe, however unlikely, cannot be ruled out completely. Some models suggest that if a strangelet were small enough, it might decay before causing any harm. Others propose that strangelets could have an electric charge that repels ordinary nuclei, preventing them from interacting in a dangerous way. On the other hand, if a strangelet were large enough and had the right properties, it could theoretically sink into the core of a planet, where its transformation of matter could go undetected until it was too late. For centuries, scientists have worked under the assumption that normal atomic matter is the fundamental building block of everything around us. The discovery of strange matter, if confirmed, would suggest that the universe might favor a completely different form of matter, one that is far more stable and long-lasting than anything we currently know. This would have profound implications for everything from cosmology to nuclear physics. The mystery of cosmic rays that shouldn't exist. Cosmic rays continuously bombard the Earth from outer space. Most of these particles are well understood. They come from sources like the Sun, or from distant supernova explosions, and their energies fall within a predictable range. Yet every now and then, scientists detect cosmic rays with energy levels so extreme that they seem to defy explanation. When a cosmic ray hits Earth's atmosphere, it sets off a cascade of secondary particles. This cascade creates a shower of subatomic fragments that spread over a wide area, and scientists use a network of detectors scattered around the globe to study these events. Most cosmic rays are relatively low in energy and have been studied for many years. But every once in a while, detectors pick up a cosmic ray that carries energy millions of times greater than the typical ones. Such events are extremely rare, but when they occur, they capture the attention of researchers worldwide. Traditional theories tell us that particles gain energy from the acceleration processes in supernova remnants, pulsars, or the shock waves generated by collisions in space. However, the energies of these mysterious particles are so high that known acceleration mechanisms seem inadequate to explain them. In some cases, the energies observed are so enormous that they exceed what most astrophysical sources can produce. This mystery has led scientists to wonder if there might be unknown or exotic processes at work in the universe. Some researchers have proposed that these particles could be the result of collisions between cosmic objects in extreme environments, such as the regions around supermassive black holes or in the jets that stream out of active galactic nuclei. In these extreme settings, the forces at play are immense and it is conceivable that particles could be accelerated to the incredible speeds required to match the energies of these mysterious cosmic rays. Other theories suggest that the sources might be even more exotic, involving processes that take place in the early universe, or in the decays of long-lived heavy particles that have yet to be observed in any laboratory on Earth. The Standard Model of particle physics is a remarkably successful theory that describes the fundamental particles and forces in the universe. However, it is known to be incomplete, and phenomena like dark matter and dark energy still elude its grasp. If these ultra-high energy cosmic rays are indeed produced by unknown mechanisms or new particles, they could provide clues to a deeper, more complete theory of nature. In this way, each detection of a mysterious cosmic ray is not just an astronomical event, it is a potential window into new physics. The vast majority of cosmic rays are harmless because the Earth's atmosphere acts as a shield, absorbing and dispersing their energy before they reach the ground. In addition, the energy carried by even the most extreme cosmic rays is spread out over an area when they interact with the atmosphere, so the effects are diffused rather than concentrated. However, if a burst of ultra-high energy particles were to strike the Earth directly, there might be local or even global consequences. Over the past few decades, facilities like the Pierre Auger Observatory in Argentina and the telescope array in Utah have been built specifically to detect and study these rare particles. These observatories use a combination of ground-based detectors and atmospheric monitoring to capture the fleeting signals left behind by cosmic ray showers. The data collected from these experiments has already provided valuable insights into the nature and distribution of high-energy particles, yet many questions remain unanswered. Scientists are still trying to pinpoint the exact sources of these mysterious cosmic rays. There is evidence to suggest that they may not come uniformly from all directions, but rather from specific regions of the sky. This anisotropy could point to certain cosmic structures, such as clusters of galaxies or large-scale magnetic fields, as the likely accelerators of these particles. Yet the details of how these structures could impart such incredible energy to individual particles remain unclear. Some models propose that strong magnetic fields in the vicinity of active galaxies might act as natural particle accelerators, while others look to more speculative ideas, such as the decay of super-heavy dark matter particles. As ultra-high energy particles travel through space, they can collide with the low-energy photons that permeate the universe in the form of the cosmic microwave background, or CMB, radiation. These collisions can cause the cosmic rays to lose energy over vast distances, a process known as the Greisen-Zarzepin-Kuzmin, or GZK, cutoff. According to this theory, cosmic rays above a certain energy should not be able to travel more than about 100 million light-years without being significantly slowed down. Yet some detected cosmic rays appear to defy this limit, arriving at Earth with energies that suggest they have traversed immense distances without losing as much energy as expected. If there is something in the universe that prevents these particles from interacting with the CMB as predicted, it could help explain why we see cosmic rays with such extreme energies. Alternatively, the apparent violation of the GZK cutoff might be a hint that our understanding of particle interactions at ultra-high energies is incomplete. Every time a detector picks up one of these particles, it is as if the universe is sending us a note written in the language of high-energy physics, an invitation to explore realms that are beyond our everyday experience. For many researchers, this is the ultimate adventure, to learn how the universe can produce such unfathomable power and to find out whether these particles are telling us something profound about the nature of reality itself. The heat death of the universe, a cold and lifeless fate. The universe, as we know it, is full of energy, where stars burn brightly and galaxies collide and reform in an intricate dance over cosmic scales. But this era of cosmic activity will not last forever. The universe is expanding, and with every passing moment, it becomes colder and more empty. If this expansion continues indefinitely, it will lead to one of the most haunting possibilities in physics, the heat death of the universe. Heat death does not mean fire and destruction, as the name might suggest. Instead, it describes a future in which all sources of usable energy have been exhausted. This fate is driven by the second law of thermodynamics, which states that energy naturally spreads out over time. Every time a star shines, every time a planet radiates heat into space, energy becomes more evenly distributed. One day, there will be no concentrated sources of energy left, no stars, no planets, no life. The first stage of this long process has already begun. The universe is expanding, and that expansion is accelerating. The cause of this acceleration is not fully understood, but is attributed to dark energy. Over billions of years, this expansion will pull galaxies so far apart that they will no longer be able to see each other. As time passes, the stars themselves will begin to die. The largest stars will go first, burning through their fuel in just a few million years before exploding in supernovae. Smaller stars, like the Sun, will last far longer, burning for billions or even trillions of years. But even these will eventually run out of hydrogen. When they do, they will expand into red giants, shed their outer layers, and collapse into dense remnants like white dwarfs. Over incredibly long timescales, even white dwarfs will fade, becoming cold, dark objects known as black dwarfs. The process will continue until there are no more active stars in the universe. Without stars, there will be no more light, no more warmth, and no more energy to sustain life. Planets will grow colder, their atmospheres freezing and collapsing as they drift through an empty and darkening cosmos. Any civilizations that still exist at this time will have to rely on artificial energy sources, but even these will not last forever. White dwarfs and neutron stars may take quadrillions of years to cool completely, but they will eventually become inert. Even black holes, the most durable objects in the universe, are not immune to the passage of time. According to Stephen Hawking's theory of black hole evaporation, black holes slowly lose energy through a process called Hawking radiation. Over unimaginable periods, far longer than the current age of the universe. Black holes will shrink, radiate away their last bit of energy, and finally vanish. By this point, the universe will be nearly empty. With all matter broken down, all stars extinguished, and all black holes gone, the only thing that remains is a thin, cold mist of subatomic particles. These particles will be scattered across a vast and silent universe, with no structures left to form galaxies, stars, or planets. Even atomic motion will slow to a near halt. This is what physicists describe as the heat death of the universe. A final state in which all energy has been evenly distributed and no work can be done. There will be no more heat to transfer, no more forces to drive movement, and no possibility of anything new arising. It is the ultimate stillness, a cosmos that exists in form but not in function, where time itself has lost its meaning. People have wondered whether anything could happen after this point. Could quantum fluctuations create new structures out of the void? Could a rare and random event trigger a new Big Bang? These ideas remain theoretical, with no clear evidence to suggest they are likely. If the laws of thermodynamics hold, the heat death of the universe is final. It is an ending unlike any other. Not a sudden catastrophe, but a slow and inevitable fading of all things into the darkness. The Big Rip, when dark energy tears everything apart. The universe is expanding. This discovery, first made in the early 20th century, reshaped our understanding of the cosmos. At first, scientists believed that this expansion might slow down over time due to the pull of gravity. But in the late 1990s, observations of distant supernovae revealed something unexpected. The expansion of the universe was not slowing down, it was speeding up. The cause of this acceleration was given a name: dark energy. For now, dark energy is relatively weak, acting as a gentle force that causes galaxies to drift away from one another over billions of years. But what if dark energy does not remain constant? What if instead it grows stronger? This is the frightening possibility known as the Big Rip. In this scenario, dark energy does not just push galaxies apart, it accelerates at an ever-increasing rate, eventually tearing apart everything in existence. The first victims of this process would be galaxy clusters. Right now, galaxies within a cluster are held together by gravity, resisting the pull of dark energy. If dark energy continues to grow, however, there will come a time when no amount of gravity can hold galaxies together. They will begin to drift away from each other at speeds faster than the pull of gravity can counteract. Next, dark energy will begin to affect individual galaxies. Right now, the Milky Way is bound together by its own gravity, with stars orbiting around the supermassive black hole at its center. But in a universe dominated by an ever-strengthening dark energy, even these gravitational bonds will eventually break. Stars will begin to drift away from their galaxies, floating alone in the vastness of space. The Milky Way, Andromeda, and all other galaxies will dissolve into scattered stars, each one moving outward at increasing speeds. The solar system itself will be pulled apart. One by one, the planets will be wrenched from their orbits, sent hurtling into the void. Even moons will be torn away from their parent planets. The destruction will not stop there. As dark energy intensifies, it will begin to affect even the bonds that hold individual objects together. Right now, the forces of electromagnetism and nuclear interactions are strong enough to hold atoms and molecules in place. In a universe governed by the Big Rip, however, even these forces will be overwhelmed. The Sun, no longer held together by its own gravity, will unravel into a swirling cloud of gas. The same fate will befall every star in the universe. Without gravity to maintain their structures, they will disintegrate, their matter dispersed into space. Then dark energy will begin to pull apart atoms themselves. Electrons, which are now bound to atomic nuclei by electromagnetic forces, will be flung away. Protons and neutrons will be torn apart as the strong nuclear force is overcome. Even these smallest known particles may not be safe. Some theories suggest that if the Big Rip occurs, it could eventually tear apart quarks. At this point, the universe will no longer resemble anything we understand. There will be no stars, no galaxies, no atoms, just an expanding void filled with particles that can no longer form structures of any kind. The very fabric of space itself may be stretched so thin that even the concept of space and time breaks down. The timeline for the Big Rip depends on the nature of dark energy. If dark energy remains at its current strength, the universe will continue expanding, but will not rip apart. If it weakens, the expansion of the universe may slow down or even reverse, leading to a different fate known as the Big Crunch. But if dark energy strengthens over time, the Big Rip could become inevitable. Some calculations suggest that if this scenario is correct, the end of the universe could come in as little as 22 billion years, far sooner than the gradual fade-out predicted by the heat-death scenario. Planck stars. Could black holes conceal something even stranger? Black holes are often thought of as the ultimate cosmic dead ends, regions of space where gravity is so strong that nothing, not even light, can escape. But some physicists believe that inside these mysterious objects, something even stranger might exist. A theoretical object known as a Planck star could be hidden deep within a black hole. According to classical general relativity, a black hole continues collapsing inward until it reaches a singularity, an infinitely dense point where the laws of physics break down. But many physicists suspect that this singularity may not actually exist. Instead, quantum effects could create an ultra-dense compact object that prevents a black hole from collapsing completely. This object, known as a Planck star, would be incredibly small, potentially just slightly larger than the Planck length, which is the smallest meaningful unit of distance in physics. One of the biggest mysteries in modern physics is the black hole information paradox. When matter falls into a black hole, it carries information about its properties, things like mass, charge, and composition. According to quantum mechanics, information should never be lost. However, General relativity suggests that once matter crosses the event horizon, that information is gone forever. This contradiction has puzzled physicists for decades. Planck stars could provide a solution. Instead of information being lost inside a singularity, it could be stored within the Planck star itself. Over vast timescales, as the black hole slowly evaporates due to Hawking radiation, the Planck star could eventually release this information back into the universe. This would mean that rather than being destroyed, the information inside a black hole is temporarily trapped and then re-emitted over incredibly long periods. An implication of this idea is that black holes might not be permanent. Instead of simply shrinking and disappearing as they radiate energy, they could eventually reach a critical point where the Planck star inside them is no longer able to hold itself together. Some models suggest that, at this stage, the Planck star could trigger a powerful explosion, releasing all of its stored energy and information in a final burst of radiation. If this were the case, it would mean that black holes do not just evaporate quietly, but might instead end their lifetimes in a spectacular event, one that could be visible across the universe. Such an explosion could resemble a gamma-ray burst. Some scientists have even speculated that certain unexplained bursts of energy we observe in space could be the final moments of ancient black holes reaching the end of their lives. Another possibility is that Planck stars could provide a bridge to other regions of space, or even to new universes. Some theories suggest that when a black hole collapses, the extreme densities inside it could create a doorway to another universe, with the Planck star acting as a kind of cosmic boundary between our reality and whatever lies beyond. If this is the case, then black holes could be portals to new realms of existence. Because they would exist deep inside black holes, they would be hidden from direct observation. However, if they do eventually explode, the radiation they release could provide clues about their nature. Future telescopes and observatories might one day be able to detect unusual energy signatures that hint at the presence of these exotic objects. While they could provide answers to some of the biggest mysteries in physics, there is currently no direct evidence that they exist. However, as our understanding of black holes continues to evolve, new discoveries could bring us closer to uncovering the truth. Whether black holes truly contain something as strange as a Planck star remains an open question, one that could reshape our understanding of the ultimate fate of information in the universe. Blitzar. Death, a neutron star's sudden and violent collapse. The gravity of neutron stars is immense, and without the force of their own rotation or other stabilizing factors, they would have no choice but to collapse even further, forming black holes. But there is one particularly eerie phenomenon among neutron stars, one that makes their eventual fate even more violent. Some neutron stars delay their inevitable collapse by spinning rapidly. This rotation generates an outward force that temporarily counteracts the crushing weight of their gravity. However, the universe is relentless. Over time, these neutron stars lose energy, slowing down bit by bit, and when their spin is no longer strong enough to resist their own gravity, they collapse instantly, triggering one of the most extreme events ever predicted. This is the death of a blitzer. The term Blitzar refers to a neutron star that has been holding itself together through sheer speed. As long as it continues to rotate fast enough, it remains stable. But the moment it slows too much, the entire structure gives way. In less than a second, the star collapses into a black hole, a process that releases an unimaginable amount of energy. The sudden disappearance of the neutron star's magnetic field leads to an enormous blast of radiation, creating what scientists believe may be the source of some FRBs. FRBs seem to come from random locations in the sky, and while some are one-time events, others repeat. The cause of these signals has been debated for years, with possibilities ranging from highly magnetized neutron stars to alien civilizations. But one compelling theory is that at least some of these bursts originate from blitzers. Unlike a typical supernova, a blitzer collapse is a silent, almost stealthy event. There's no bright flash of light, no expanding cloud of debris, just a brief but powerful burst of energy. mainly in the form of radio waves and possibly gamma rays. The star is there one moment and gone the next. These collapses could, in theory, happen anywhere in the universe, including relatively close to us. If a Blitzar were lurking within a few thousand light-years of Earth and collapsed, the resulting radiation burst could potentially damage the ozone layer if they struck Earth directly, exposing the planet to harmful cosmic radiation. However, most FRBs detected so far appear to be coming from galaxies millions or even billions of light-years away, meaning any known blitzers are not an immediate threat. Scientists are currently searching for closer candidates. If neutron stars in our own galaxy are on the verge of turning into blitzers, we might be able to detect signs of their impending collapse. Astronomers study pulsars, neutron stars that emit beams of radio waves, to monitor how fast they are spinning. If a pulsar slows down to the critical point where its own mass can no longer support itself, it could become a blitzar at any moment. Given that neutron stars are already abundant, hundreds of millions likely exist in the Milky Way alone, there could be more blitzers out there than we realize. Some may be teetering on the edge of collapse right now, silently spinning down until they reach the point of no return. Other stellar catastrophes, like supernovae, often have precursor events, instabilities, flashes of light, or mass ejections that hint at an impending explosion. But a blitzer's collapse happens almost instantly. There is no brightening phase, no gradual build-up. The only sign that it has happened at all is the sudden burst of energy that follows. If a blitzer collapse were to occur close enough to Earth, what would we experience? The good news is that, even at their most extreme, these events are unlikely to pose an existential threat. A gamma-ray burst from a blitzar could, in theory, affect the atmosphere if it hit directly. But it would have to be very close, within a few hundred light-years, to cause any real damage. Given that we haven't detected any known neutron stars on the verge of collapse within that range, the risk remains theoretical. Future radio telescopes, such as the Square Kilometre Array, will help astronomers detect more FRBs and determine their sources with greater accuracy. Until then, these unseen time bombs continue to spin in the dark, waiting for the moment when their time runs out and they vanish into the abyss. Bosen stars. Could these exotic objects mimic black holes? Out in space, some of the most powerful objects in the universe are practically invisible, detectable only by their gravitational influence. Black holes are often thought to be the ultimate unseen giants. But what if something else, something even stranger, was lurking out there? Something that looked like a black hole, but operated by entirely different physics. Unlike black holes, which form from the collapse of massive stars, Bosen stars would not be made of ordinary matter at all. Instead, they are thought to be composed of bosons, particles that follow different physical rules than the fermions that make up normal atoms. While no one has ever observed a boson star, theoretical models suggest that they could exist in a state where quantum mechanics and gravity interact in bizarre and unexpected ways. One of the strangest things about boson stars is that, unlike black holes, they wouldn't have an event horizon. Instead, a boson star would be a massive, dense, but still somewhat diffuse structure. From a distance, its gravitational pull could mimic that of a black hole, bending light and warping space-time in much the same way. A star orbiting a boson star might behave as though it were circling a black hole, yet the boson star itself would remain nearly invisible, glowing faintly only through the radiation it might produce as particles interact near its surface. Some scientists have proposed that the supermassive black holes believed to exist at the centers of galaxies might not be black holes at all. Instead, they could be enormous boson stars, millions or even billions of times the mass of the Sun. If this were true, it would fundamentally change our understanding of how galaxies form and evolve. Another possibility is that boson stars could be connected to the mystery of dark matter. Since boson stars wouldn't interact with light in the same way that normal matter does, they could potentially be a form of dark matter, massive but nearly invisible objects scattered throughout the universe. If this were the case, then some of the missing mass in galaxies, which astronomers currently attribute to invisible dark matter, might actually come from an undiscovered population of Bosen stars. Theoretical studies suggest that Bosen stars could come in different forms. Some might be extremely compact, resembling black holes so closely that even a detailed gravitational wave signature might not distinguish them. Others might be much larger, diffuse objects spanning vast distances with only a weak but detectable gravitational pull. In some models, Bosen stars could even be hollow in the sense that their mass is spread out in a cloud-like structure rather than concentrated in a single point. Since they don't emit much radiation, spotting them directly would be extremely difficult. However, there are ways we might be able to detect them indirectly. One method would be through their gravitational lensing effects, the way their mass bends and distorts the light from background objects. If a Bosen star passed in front of a distant galaxy, for example, its gravity could create a strange and unique lensing pattern, different from what would be expected from an ordinary black hole or other massive object. Another way is through gravitational waves. When two black holes collide, they produce ripples in spacetime that can be detected by observatories like LIGO and Virgo. If two Bosen stars were to merge instead, the resulting gravitational wave pattern might look slightly different from a typical black hole collision. Detecting such a signal could be the key to proving that Bosen stars exist. If a Bosen star were located near a normal star, it could gradually pull material away from it, forming an accretion disk similar to those seen around black holes. However, because a Bosen star lacks an event horizon, the way this material behaves might be different from what we would expect near a true black hole. Some scientists have speculated that Bosen stars could even be linked to the origin of the universe itself. In certain models, the early universe may have been filled with exotic particles, some of which could have clumped together to form primordial boson stars. These objects, if they still exist, could be relics from the very first moments after the Big Bang, providing insight into physics that goes beyond our current understanding. Gravastars, a theoretical alternative to black holes that might be even weirder. The idea of gravastars was first proposed in 2001 by physicists Paul Mazur and Emil Motola. They were searching for a way to describe what could happen if a star collapsed under its own gravity but did not form a singularity. In their model, instead of a black hole forming, the intense gravity would create a bizarre quantum state inside the object, preventing it from collapsing completely. This would result in an object that appears almost identical to a black hole from the outside, but behaves very differently at its core. The traditional model of black holes creates an event horizon. While this model is widely accepted, it creates major problems when combined with quantum mechanics, including the information paradox. A gravastar could be an alternative solution to this problem. Instead of forming a true singularity, a collapsing star might transform into a gravastar, a strange object with an ultra-dense shell and a mysterious interior. Inside this shell, space itself would be filled with a form of energy called a quantum vacuum. This vacuum would exert negative pressure, counteracting gravity and preventing the formation of a singularity. In this way, the gravastar could exist as a stable object, avoiding the infinite density of a black hole while still maintaining an incredibly strong gravitational field. Its gravitational pull would be just as intense, meaning that light and matter would behave around it in the same way they do around a black hole. If an observer were watching a gravastar from far away, they would have no way of telling the difference. However, a closer look might reveal some key differences. Unlike a black hole, it would not have a true event horizon. Instead, it would have an incredibly dense outer shell that prevents anything from falling inside. Matter approaching a gravastar might bounce off its outer layer rather than being swallowed into a singularity. If gravastars are real, they provide new insights into quantum gravity, the nature of space and time, and even the ultimate fate of the universe. Some theories suggest that gravastars might not be permanent objects, but could eventually transform into something else. If the exotic quantum vacuum inside a gravastar were to collapse or change state, it could trigger an event unlike anything seen before in astrophysics. Some have even speculated that such an event could be related to the Big Bang itself, suggesting that the universe might have been born from the collapse of a previous gravastar-like object. Despite the intrigue surrounding them, they remain theoretical, as there is no direct evidence for their existence, and many physicists are skeptical of the idea. The traditional black hole model is well supported by observations, and while it does present some paradoxes, many researchers believe that these can be resolved without invoking an entirely new type of object. However, the possibility of gravastars still remains open, and as our ability to observe the universe improves, we may one day find evidence that supports their existence. Cougal blitz, a black hole made of pure light. A black hole is a place where matter has been crushed into an infinitely dense point. But there's another way a black hole could theoretically form, one that doesn't involve matter at all. A Cougal blitz is a black hole created entirely from light. It wouldn't be formed from a dying star, but instead from an enormous concentration of pure energy. In theory, if enough radiation were packed into a small enough space, its energy density would be so great that it would warp space-time just like a traditional black hole. The idea comes from Einstein's famous equation E equals mc squared, which shows that mass and energy are interchangeable. In a normal black hole, mass provides the gravitational force that causes collapse. But since energy has mass equivalence, an intense enough concentration of light or radiation could create the same effect. If an unimaginable amount of photons were focused into a single point, the energy would bend space so drastically that it would form a Cougal blitz, a ball lightning of pure radiation that collapses under its own gravity. Unlike black holes formed from stars, a Cougal blitz wouldn't need matter to exist. Once it formed, it would behave just like any other black hole, trapping anything that crossed its event horizon. It would have the same ability to warp time, distort space, and swallow anything that came too close. But it would be made entirely of energy, with no physical material involved in its creation. If such an object could be formed, it would be an incredibly powerful energy source. Some theorists have suggested that an advanced civilization could create Cougal blitzes on purpose, using them as power stations. A Cougal blitz would be one of the most efficient energy sources possible, producing vast amounts of Hawking radiation as it slowly evaporated. If a civilization had the ability to generate and control such an object, it could provide energy on an almost unimaginable scale. Some speculative designs for futuristic spacecraft suggest using small artificial black holes to generate thrust. A spacecraft equipped with a Cougal blitz drive could theoretically feed mass into the black hole and use the resulting energy to propel itself forward. Unlike chemical rockets, which are limited by the amount of fuel they can carry, a Cougal blitz-powered ship could have a nearly endless energy supply. But while Cougal blitz black holes could be a source of power, they could also be weapons of unparalleled destruction. A black hole, even a small one, is one of the most dangerous objects in the universe. If a Cougal blitz were to be created and released in an uncontrolled way, it could consume everything in its vicinity. The gravitational pull of even a tiny Cougal blitz would be enormous, and if it were allowed to fall into a planet, it could burrow through the core, devouring matter as it moved. Some calculations suggest that a Cougal blitz could be used as a doomsday weapon far more devastating than any nuclear bomb. Unlike a conventional explosion, which releases energy outward, a Cougal blitz would continue consuming matter, growing larger as it fed. If an advanced civilization had the capability to create and control Cougal blitzes, it could theoretically use them to destroy entire planets or even stars. A targeted Cougal blitz attack could eliminate a solar system, leaving behind only an ever-growing black hole in its place. The amount of radiation required to form a Cougal blitz is beyond anything humanity could currently produce. Even the most powerful lasers on Earth generate only a tiny fraction of the energy needed. To create a Cougal blitz the size of a single proton, one would need to concentrate more energy than is currently produced by all the stars in our galaxy. Such a feat would require technology far beyond anything we possess today. During the first moments after the Big Bang, the universe was filled with intense radiation. Some physicists have speculated that areas of extreme energy density might have collapsed into primordial Cougal blitz black holes. If that happened, those black holes could still be out there today, lurking unseen in the darkness of space. If a black hole can be created purely from energy, does it suggest that the laws governing black holes are more universal than we thought? Could other forms of energy create similar objects under extreme conditions? Some physicists believe that investigating Cougal blitzes could help resolve some of the mysteries of quantum gravity and the relationship between energy and space-time. Pair instability supernovae, when stars obliterate themselves completely. Most stars that explode as supernova leave something behind, a dense neutron star, or if the original star was massive enough, a black hole. But there is another type of stellar explosion so powerful that it leaves absolutely nothing behind. A pair instability supernova is a detonation so complete that even the core of the star is obliterated. It is one of the rarest and most extreme fates a star can undergo, but when it happens, it reshapes all space around it. In most stars, the outward pressure from nuclear fusion balances against gravity, preventing collapse. But for the most massive stars, those more than 130 times the mass of the Sun, things work differently. When the core of such a star reaches temperatures above a few billion degrees, the usual laws of stellar stability begin to break down. At these extreme temperatures, high-energy gamma rays fill the core. Normally, these gamma rays help support the star by providing radiation pressure, pushing outward against the force of gravity. But when the energy of these gamma rays becomes too high, something strange happens. They begin spontaneously transforming into pairs of particles, electrons and their antimatter counterparts, positrons. This is the process known as pair production. By converting gamma radiation into matter, the star suddenly loses a critical part of its outward pressure. With less radiation pushing outward, gravity briefly wins. The core contracts rapidly, triggering a runaway fusion reaction. In a normal supernova, this collapse would lead to the formation of a neutron star or a black hole. But in a pair instability supernova, there is no such remnant. Instead, the sudden compression forces the remaining fuel in the star to undergo explosive fusion all at once. The result is a detonation of such force that the entire star is torn apart in a single, final burst of energy. All of its material is expelled into space, enriching the surrounding region with heavy elements. The energy released in a pair instability supernova can be hundreds of times greater than that of a typical supernova. This makes them some of the most luminous explosions in the universe, visible from billions of light years away. Because of the extreme conditions required, pair instability supernovae are thought to be rare in today's universe. They likely occurred more frequently in the early universe when massive stars were more common. The first generations of stars, known as population 3 stars, were composed almost entirely of hydrogen and helium. Some of these stars may have been massive enough to undergo pair instability, helping to seed the cosmos with the heavier elements necessary for the formation of planets and life. But while they are less common now, they are not impossible. Astronomers have identified candidates for modern pair instability supernovae, including one of the most powerful stellar explosions ever observed, SN 2006 GY. This supernova, detected in 2006, released an astonishing amount of energy, leading scientists to suspect it may have been the result of a pair instability event. Another supernova, SN 2016 APS, was even brighter. If a pair instability supernova were to occur relatively close to Earth, it would be an event unlike any other. The sheer brightness of the explosion would outshine the combined light of all the stars in its host galaxy. The high-energy radiation released would be immense, and while most of it would be absorbed by interstellar space, it could have effects on planetary systems within a certain range. If a star in our galaxy were to undergo this fate, it could create a shockwave of particles moving at extreme speeds, affecting nearby stars and possibly influencing planetary atmospheres. Fortunately, the conditions required for a pair instability supernova are so extreme that only a small number of stars in the modern universe are even capable of it. But studying these rare explosions helps scientists understand the life cycle of the most massive stars and provides insight into the violent events that shaped the cosmos. Without them, the universe might have remained filled with only the simplest elements, never forming the complex chemistry needed for life to emerge. These violent deaths of stars, as destructive as they are, have helped create the very materials that make up everything we know. Fast blue optical transients, the mysterious supernovae that appear and disappear. The universe is full of explosive events. Supernovae, gamma-ray bursts, and neutron-star collisions light up the cosmos with bursts of energy that can be seen across vast distances. But in recent years, astronomers have observed something even stranger. Brilliant flashes of light that appear suddenly, burn intensely for only a few days, and then disappear as if they were never there. These mysterious events are known as fast blue optical transients, or FBOTs, and they do not behave like any known cosmic explosion. Unlike traditional supernovae, which can take weeks or even months to fade away, FBOTs reach peak brightness in just a day or two before rapidly dimming. They also emit an unusually strong blue light, indicating extremely high temperatures. Some produce powerful radio waves and X-rays, while others seem to vanish without leaving behind a trace. What is powerful enough to create such an event, yet unstable enough to disappear almost immediately? The first confirmed FBOT was detected in 2018 and was given the unusual name, the Cougal. This explosion, located about 200 million light-years away, was incredibly bright, up to 100 times brighter than a typical supernova, but faded far too quickly. At first, scientists assumed it was just an unusual type of stellar explosion, but as they examined the data more closely, things didn't add up. The explosion produced an immense amount of high-energy radiation, including X-rays, which suggested that something more extreme than a normal supernova was occurring. Even more puzzling, there was no clear evidence of an expanding shell of debris, as seen in traditional supernova remnants. After the Cougal, other FBOTs were discovered with similarly strange properties. Each new detection only deepened the mystery. Some of these events emitted incredibly powerful radio waves, indicating that they had somehow ejected material moving at near-light speeds. Others produced rapid pulses of X-rays, almost as if something at the heart of the explosion was continuously re-energizing it. Scientists struggled to explain what could produce such a chaotic event. One of the leading theories is that FBOTs could be a type of failed supernova. Normally, when a massive star runs out of fuel, it collapses, triggering a supernova. In some cases, the core of the star may collapse directly into a black hole with little or no outward explosion. But with FBOTs, something different seems to be happening. These stars may be experiencing a partial explosion, one that releases an enormous burst of energy but does not completely destroy the star. Another possibility is that FBOTs are created when a star is shredded by an intermediate mass black hole. When a star gets too close to a black hole, the immense gravitational forces can rip it apart, creating a brief but powerful burst of energy. If this process happens under the right conditions, it could explain the extreme brightness and rapid fading of these events. However, most known black holes are either stellar mass, meaning a few times the mass of the Sun, or supermassive, some millions or billions of times the Sun's mass. And scientists have yet to confirm the existence of intermediate mass black holes in large numbers. Some researchers believe that FBOTs might be an entirely new kind of cosmic explosion, one that does not fit into the traditional categories. One hypothesis is that they could be caused by the sudden collapse of exotic objects like neutron stars or magnetars. Magnetars are known to produce bursts of X-rays and gamma rays, If a magnetar were to collapse into a black hole, it could release an intense flash of energy before vanishing completely, which would match some of the characteristics of FBOTs. There is also speculation that FBOTs could be related to something even more exotic, perhaps even a new type of matter interaction or unknown physics. Some FBOTs seem to emit a large amount of energy without producing a visible expanding cloud of gas. This could mean that they involve some kind of highly efficient energy conversion process that does not rely on normal matter behaving as expected. The most curious aspect of FBOTs is that they appear unpredictably and fade too quickly for detailed study. They do not seem to have a clear pattern. Some appear in regions of space where no massive stars are expected to exist, while others have been found in environments rich in gas and dust. The randomness of their locations only adds to the mystery. For now, FBOTs remain a puzzling enigma. Scientists are watching the sky closely, hoping to catch more of these fleeting flashes before they disappear into the darkness once again. The brain in a vat hypothesis. Are we just cosmic experiments? Imagine waking up one day to the realization that everything you've ever known, your thoughts, your experiences, your memories, aren't real in the way you think they are. What if your entire perception of reality was nothing more than an illusion, carefully constructed by something far beyond your understanding? This idea, known as the brain in a vat hypothesis, is a modern variation of a question that has haunted philosophers and scientists for centuries. How can we be sure that what we experience is real? At its core, the brain in a vat hypothesis suggests that consciousness itself could exist within an artificial environment, sustained by external forces we cannot detect. In this scenario, a disembodied brain, kept alive in a life-supporting vat, could be fed electrical signals that perfectly simulate reality. To the brain, the experiences would feel completely real. The sights, sounds, and sensations it perceives would be indistinguishable from those of a person walking freely in the real world. If the signals were precise enough, the brain would have no way of knowing it was not truly interacting with an external reality. The brain does not directly experience the world. It interprets sensory inputs that are transmitted by the nervous system. The taste of food, the warmth of sunlight, the sound of music. These are all just electrical impulses processed by neurons. If a sufficiently advanced system could replicate these signals, then in theory a brain floating in a vat could believe it was living an ordinary human life, never suspecting that its entire world was an illusion. Some take this idea even further, proposing that we might not even need biological brains for this to be possible. If consciousness arises from complex patterns of information processing rather than from the physical structure of a brain, then a sufficiently advanced computer simulation could achieve the same result. A digital consciousness running on an advanced system could experience an entire lifetime of thoughts, emotions, and sensations without ever realizing that it was nothing more than a collection of data inside an artificial construct. The brain in a vat hypothesis is closely linked to the broader simulation hypothesis, which suggests that our reality could be a carefully designed program created by an advanced intelligence. If a civilization had the ability to simulate conscious beings, it might create vast digital universes as experiments, simulations, or even entertainment. To those inside the simulation, everything would appear as real as any physical universe. Some argue that, statistically, such a scenario might not only be possible, but likely. If it is possible to create realistic conscious simulations, then a sufficiently advanced civilization could create millions, or even billions, of simulated worlds. If that were the case, then the number of simulated beings would vastly outnumber the number of real beings. By that logic, the chances that we ourselves are part of the one true physical universe, rather than one of countless simulations, would be extremely small. There have even been scientific discussions about how one might test whether reality is a simulation. Some theorists propose looking for computational glitches in the universe, small inconsistencies that might suggest an underlying artificial framework. Others suggest that if reality were simulated, it might have built-in limitations, such as a finite resolution for space and time, much like pixels in a digital image. Certain quantum effects, such as the apparent pixelation of space at the smallest scales, have even been cited as possible clues that reality is not as continuous as it seems. Proving or disproving such a theory is an enormous challenge. If an advanced intelligence had the ability to simulate a reality as complex as our universe, it could also ensure that the simulation never revealed itself. Any errors in the system could be corrected before they became noticeable. The very idea of looking for proof assumes that the creators of the simulation would allow such proof to exist in the first place. Some take a more unsettling view, suggesting that if we are in a simulation, there could be unknown rules governing its operation. Perhaps the simulation has a purpose that we cannot comprehend. Maybe it is an experiment designed to test different possibilities of human development. Maybe it is a training ground for minds that will one day wake up into a higher reality. Or perhaps we are simply entertainment for beings so advanced that our struggles and achievements are nothing more than a passing curiosity to them. If reality is not what we think it is, does anything we do truly matter? Would our emotions, relationships, and experiences have any significance if they were simply programmed responses? Or does meaning exist regardless of the nature of reality? For some, this idea is deeply unsettling. It suggests that we are not in control of our own fate and that the rules of existence are set by forces we will never understand. If we are in a cosmic experiment, then perhaps the ultimate question is not whether we are real, but what the purpose of the experiment might be. Hellish planets that rain. Metal and glass. There are planets in the universe so hostile that even the most extreme conditions on Earth seem mild in comparison. These are worlds where storms do not bring water or ice, but molten metal and shards of glass. The heat is so intense that the air itself carries vaporized metals, and the winds are strong enough to turn these elements into deadly storms. If a spacecraft were to descend into one of these planets' atmospheres, it would be met with a sky filled with liquid iron and a sea of molten rock. One of the most famous of these extreme worlds is WASP-76b, a gas giant located about 640 light-years from Earth. This planet orbits its star so closely that it is tidally locked, meaning one side always faces the star while the other is locked in eternal darkness. The day side reaches temperatures of around 2,400 degrees Celsius, or about 4,350 degrees Fahrenheit, which is hot enough to vaporize metals like iron. In this inferno, the iron turns into gas, rising into the atmosphere like water vapor does on Earth. But as the planet rotates, strong winds carry this superheated iron vapor to the cooler night side, where temperatures drop to around 1,500 degrees Celsius, or about 2,700 degrees Fahrenheit. There, the vapor condenses and falls back down, not as rain, but as molten iron droplets. If a human were standing on the planet's night side, they would witness an endless downpour of liquid metal, hot enough to melt anything in its path. On our planet, rain is made of water because it evaporates, forms clouds, and then falls when it cools. On WASP-76b, the same cycle happens, but with iron instead of water. The planet is so hot that even rock-like materials can exist as gas in its atmosphere, creating a bizarre and deadly weather system. If a spacecraft were ever to approach, it would need heat shielding unlike anything ever built. Protection not only from the immense radiation of the nearby star, but also from the possibility of metal rain striking at extreme speeds. HD 189733b, a planet about 64 light-years away, is home to another terrifying storm system. Instead of metal, this planet's atmosphere is filled with silicate particles, tiny grains of rock. The winds on this world reach speeds of up to 8,700 kilometers per hour, or around 5,400 miles per hour, far faster than the speed of sound. In such conditions, the silicate particles are picked up by the winds and flung across the atmosphere, creating storms of liquid glass. The result is a sideways rain of razor-sharp glass shards cutting through anything in their path. If a human were somehow exposed to the elements of this planet, they would be shredded apart in an instant as the high-speed winds hurled thousands of tiny glass fragments against them like a sandblaster operating at unimaginable intensity. Spacecrafts would need to be armored against constant impacts from glass particles, moving at supersonic speeds. Any surface structures would need to be built from materials stronger than anything currently available, resistant to both the extreme winds and the abrasive forces of airborne silicates. Advanced robotics would struggle to operate in such a world, as delicate instruments would be quickly worn down by the relentless storm. Scientists have theorized the existence of planets so hot that their atmospheres contain elements we normally associate with solid rock. Some of these planets, classified as ultra-hot Jupiters, reach temperatures exceeding 3,000 degrees Celsius, making their atmospheres rich in vaporized metals like titanium, aluminum, and even elements like vanadium. These planets may have clouds made of iron, aluminum oxide, or even titanium compounds. Even more exotic is the possibility of carbon planets, worlds where carbon, rather than oxygen or silicate materials, dominates the surface and atmosphere. In these extreme environments, the weather could involve storms of pure carbon, possibly even raining graphite or microscopic diamonds. If such planets exist, their skies might be filled with soot-like carbon clouds, and their surfaces might be covered in a thick layer of tar or diamond dust. The physics behind how vaporized metals condense into liquid and fall as rain is the same physics that governs how water behaves on Earth. Understanding these alien storms could help astronomers refine their models of planetary atmospheres, making it easier to detect worlds that might actually support life. The existence of such planets raises a question. Could anything survive in such an environment? On Earth, life has adapted to survive in conditions once thought impossible. Boiling hot hydrothermal vents, acidic lakes, and even radioactive waste sites. But the worlds of molten iron rain and glass storms push the boundaries of what life could endure. Any form of life on these planets, if it exists, would need to be built from materials far beyond anything found on Earth. Its cells would have to resist extreme heat. Its biochemistry would have to function in an environment where water is non-existent, and its very structure would need to withstand the most violent weather conditions in the universe. These exotic life forms might not rely on carbon-based chemistry like life on Earth does. Instead, they might be based on silicon, tungsten, or other heat-resistant elements. If such life exists, it would not resemble anything we have ever seen. It would be a form of life designed not to avoid fire and destruction, but to thrive in it. One day, as technology advances, we may be able to send probes to these distant worlds, allowing us to witness their deadly beauty up close. What we find there could change our understanding of what a planet can be, and perhaps even redefine the limits of life itself. Which of these nightmarish objects do you find the scariest? Or was there something we missed? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.